this computer. Oh, good. Okay. I think everyone is joining now. Maybe I should wait for a couple more minutes. Hello, good morning, everyone.
Hi, Clark. Hi, everybody. How are you?
Hi, very good. Thank you. Hi. Okay, all right. Then maybe I should start. Okay, good morning, everyone. Thank you for joining our tutorial, Explainable AI for Software Engineering. So today, my name is Clark Chakrit Tantitam and Jirayut. So Jirayut, do you want to say hi to everyone?
Good morning, everyone.
Good morning. Yeah. Okay. So both of us will do the tutorial today together about the new topic about sustainable AI for software engineering. Okay? So if you would like to learn more, we actually write a course note at the website xai4se.github.io. If you have time or if you are interested, please check it out as well. Okay, so before I start my talk, I just want to acknowledge my colleagues and my collaborators who support my research in the past few years. I think this topic is quite topical, but it has been rarely explored. It still remains challenging, you know. So I just want to say thank you to everyone who support my research. Yeah. So if you have any questions, you can ask questions in the Zoom chat, but after the tutorial, you can send me an email if you have any questions or ask me on the Twitter as well. And again, the materials are available online at the xai4se.github.io. So, and the tutorial is developed by both of us, Jirayut and I. It can be accessed anytime and anywhere. It is written using the Jupyter book. That means all the code are executable. If you click the binder or the collab, you can run the code on the web as well without any installations or dependencies. So I think this is this tutorial. This book is quite handy and accessible. Yep. So before I start my talk, I just want to remind you that this tutorial is not a comprehensive introduction to explainable AI theories or the algorithms. And this is not an exhaustive survey of the explainable AI as well, because there is a lots of bodies of research about this area. I think it has been getting booming around 2016. So up like 5 years later, I think it should have more than 1,000 papers. And those topics have been published in many disciplines as well, like AI, machine learning, HCI, social science, and software engineering. So we cannot cover everything. And we are software engineering researchers that try to make the AI for software engineering research more explainable and more actionable for practitioners. So they can be widely adopted in practice or industry. So that means that this tutorial aims to motivate why the XAI is very important in software engineering and what is the concept behind. So I just want to provide the key important aspect about the explainable AI. And finally, I just want to demonstrate some potential applications of the XAI for SE as well. Yep. And finally, Kashumi. Hello, can everyone please mute? Yep, thank you. So, and finally, I just want to convince everyone to tackle about this topic because there are lots of open research questions and challenges about the explainable AI for SE. Yep. So the agenda of my talk today has 3 parts. First, I will talk about what is the explainable AI for software engineering. I will show some live demo as well. And then I will discuss about what are the potential usage scenarios. And finally, I will wrap up with the lessons learned and the open questions. So, in general, software development involves lots of complex and critical decision making. For example, as a managers, normally people should ask like when should we release the software. As a developers, during their programs, during their development period, they also ask like how should I fix this bug? And as a QA engineers, they also need to answer like they also ask like which modules should I test first? And as a designer, they also ask lots of questions like, is software design good enough or not? As a tester, how effective is our test suite? So there are lots of questions behind, but at the moment, there is no analytics. There's no like, without analytics, any erroneous in the decision making can go wrong, go badly, you know, like it will make the companies very costly. It will impact the reputations of the companies as well. So recently, AI and the machine learning is widely adopted in software engineering and software companies. So in general, they can use the AI and the machine learning to improve the software quality. For example, they can use to predict where the defect is, or to predict the vulnerabilities, the malware, or they can also use to generate the test cases as well. Like and on the figure on the right side is example, successful example. For example, Ubisoft integrate the defect predictions into their development lifecycle to predict bugs for every commits. And Sapfix and Sapiens also adopt the AI tools to find and fix software bugs as well. And the AI and the machine learning can also be used to improve the development productivity. For example, use the like a computer vision technique to generate the UI or generate your UI code, requirements, code comments, predict the developer's stream productivity, or use the AI machine learning to recommend who should fix this bug, who should review the code, like developer recommendation task or the reviewer recommendation task. We can also use the AI and the machine learning to predict or identify who the developer turnover as well. So there are lots of successful of the AI, lots of success about the AI and the machine learning in software engineering. But I just want to show an example of the defect prediction, like why it matters. So just to give an overview, what is the defect prediction? Normally, developers, when you submit a code or pull requests to the GitHub repositories, reviewers have to review the code and ensure that the code or the new contributions in the pull request are of high quality, so it can be integrated into the software development branch, the master branch. However, the problem is that at the moment in the large scale complex software projects, there are too many pull requests and there are too many, and each pull requests are very large as well. Then, so the first question for as a reviewer or a tester or QA is that which pull request that they should look at it first. So that's why defect prediction models, which is an AI or ML model to predict which areas of the code are the most risky or the clean. So they can prioritize the limited QA resources on the most risky one, you know. And so far, and the concepts of the defect prediction has been proposed for more than 10 or 20 years. And I can see lots of integrations of the defect prediction models in many software companies, including Google, Microsoft Research. And recently, I also see the Microsoft Code Defect AI, which is a new product from Microsoft AI team as well, including the Amazon Code Guru. However, most of the time when we talk to practitioners, they often ask the questions why a commit is predicted as defective and why this file is predicted as bug, whether I should trust the AI or machine learning model or not. And given this file that is predicted as a bug, then they also ask the questions like, then how should how should I improve the quality of this one, right? So there are lots of questions, and a lack of explainability or actionability of the defect prediction models often lead to a lack of trust, which leads to the a lack of adoption in practice as well. So that's why the concepts of the explainable AI is emerged recently, and the objective of the explainable AI is to create a suite of AI and machine learning techniques that produce a more explainable model while maintaining a high levels of prediction accuracy. And it also enables the human users to understand and build an appropriate task to the predictions as well. So I just want to show you an example. Like in the past, we have lots of data, the big data from the GitHub. We feed this kind of data into the AI algorithm. We produce the model. And then this kind of models, yes, of course, it can produce lots of decisions or recommendation to the end users. But most of the time, they often ask the question like, why did you do that? Why not something else? Or what to do, right? But what if we can have another kind of technique that is more explainable, and then the end users may understand more, like why the model makes kind of predictions. Okay. So there are lots of confusions in the community as well between the term interpretable machine learning and the explainable AI. From the common definition, from what I graph from literature survey, they define that the interpretable machine learning, it means that you use a white box model. It's not complex at all, but they are very highly interpretable by itself. So it should be used for like a high-stake decision making. These kind of techniques include the decision tree or logistic regression. So they are just a simple mathematics, but you understand what is inside the model and how each decision is derived from the mathematical models. However, these kind of techniques are not that accurate, Then that's why recently, lots of researchers often use neural machine learning, deep learning. They are very, very accurate, but they are often treated as black box. Then how can we explain it? Okay. So that's why we propose a new technique. So it's called PyExplainer. This paper is published at the ASE conference and also received the ACM 6 Distinguished Paper Award as well. So this technique, the definition of this work, of this technique is a local rule-based model agnostic technique to generate the explanation and the actionable guidance. That's the main goal. Okay. In the past, in the field, in the earlier slides, we already mentioned that the defect prediction models are not explainable at all. And then I'm going to show you how to make it more explainable and how can we generate the actionable guidance to the developers. Okay. So given the defect model, so next I am going to show you how it works. Given the defect prediction models, normally, and the instance to be explained, or a file or a commit. So basically, we just take these two input into the PyExplainer, and the PyExplainer will generate the rule-based explanation. For example, this is an example output. If churn, so like this one, churn is greater than 100 and reviewers less than 2 is associated with the defect. So it means that this kind of rule-based explanation is used to answer the question why a commit is predicted as defective. So this one is predicted as defective because the churn of this commit is too large it is greater than 100, and it has less than 2 reviewers, review the code, review this commit, right? Then the developers know, okay, what's wrong? What is the most important aspect? Okay, so this kind of knowledge is very important to help QA or developers understand what went wrong with this commit, so they can focus on the most important aspect instead of fixing something else, right? And this kind of rule-based explanation actually goes beyond the traditional feature importance. It doesn't, the feature importance just show which feature is the most important, but it doesn't tell you what is the risk threshold, like how large is large, how small it should be, you know. So this kind of rule-based explanation is very useful in this context. Okay. And once we know the explanation already, then we also think about like how can we make the explanation more actionable as well. Okay, so once we have this kind of explanation, yes, it is explainable, but it's still not understandable and not actionable yet. So that's why we design a proof of concept of the interactive PyExplainer visual explanation. Okay, and this is an example which is going to be in the Jupyter notebook. Okay, so given a commit, given a model, once we feed these two into the PyExplainer, it will tell you what is the risk score, how risky it is of this commit that will be defective in the future, and it will tell you the explanation. Okay, so the rules explanation will be translated into the slide bar, into this kind of visual, and it will tell you, yeah, what's wrong. Okay, an example of this one is that, for example, the explanation is the value of the line added is more than 155, so that means it should be is too large, so it should be reduced, something like that. So this is a risk score. This is the explanation and the guidance. And the cool thing about the PyExplainer is that the question from the developers, they often ask the question, what if we change this? Would it reverse the prediction or not, right? So let's say if the explanation, the rule here, churn is greater than 100, and then the question, then how small it should be, right? What if we change to the 80, to the 70, to the 50? Would it reverse the prediction or not? So this kind of interactive visualization, it will help developers make a better decision how to identify the appropriate value of that factor. So this kind of tool, if we change the slide bar here, the score will be updated immediately as well from the model. Okay. So far, anyone has questions? Let me just, will the slide be available? Yes, it will be available. Okay, no more questions. Then next step, I am going to do a live demo of the PyExplainer. So basically, everyone can go to this URL, xai4se.github.io/tutorials /PyExplainer-live-demo.html. So Jirayut, maybe can you put the link in the Zoom chat so everyone can access as well? Thank you. And so if you go to this one and go to the on the left side, there's a menu title ASE'21 PyExplainer live demo. Click that one, and then you click the binder. Okay. So I am going to show you the live demo, the code here. So this is an example. Does everyone see my screen? Yes. Okay. I mean the Jupyter one. Okay. Yes. Okay.
Yes, we can see.
Yes. Okay. So this is a live demo. Okay. I'm going to explain the concept here. Let's say this is the context of the defect prediction. Let's say we input the train data set here, the leucine 2.90 .csv and the test data here. So that means 2.9 we already know. Oh, okay, 1 second. Maybe I should run this one again. Yep. Yep. So we have the training data here, the leucine 2.9.0 that we release, and the test version, the future one, okay, 3.0.0. And then we already have the feature that we want to predict whether a file is above or not. And then we also have the predicted feature here. So we use the code ownership, the numbers of class couple, the numbers of average lines, and the ratio comment to code. This is just an example. In reality, you may have lots of features. Oh, geez, what's wrong? Yep. Okay. Yep. Run. Okay. Yep. So we already have the data set here. We define which columns are the outcome that we want to predict and what are the features that we want to use. We pre-process something, and let's say if we are going to build the model. Okay. First, we are going to construct a random forest model using the code above. We already define what is the training data and the testing data here. So we're going to try to build the model. Everyone, please try to support me if it is going to work or not. Yep. So first, we can build the random forest model based on the variables that we already defined above. Okay. And the concepts of the apply explainer, it is very simple. It has only like 1 or 2 steps. Okay. First, we need to define the, first we need to import the library. That's very important. And then we select which file that we want to explain. Let's say this is an example 1. And first we need to build a local model from the PyExplainer package. Okay. Yep. So the input here should be the training data and which feature, the independent variables, which columns that we want to use as a features, and which column that we are going to use as a outcome that we want to predict, and what is the random forest model. Oh, which model? Okay. Yep. So first, we need to build the PyExplainer object here, and then the next step is to generate the explanation. Okay. Yeah, to generate the explanation. So that means we just want to explain this instance, okay? This file, the file to be explained, and we need to define what is the search function, which I am going to explain later, and some parameters here. So if you run it successfully, it will take some time. Yep. So if it is run successfully, and then in the last step, if you run the PyExplainer visualize to visualize the rule here. I will go back to this one later once it is ready. It will show you an interactive visualization like this. Okay, so that means this file is predicted as buggy because the count, the numbers of class couple is greater than 39. It is too large, too much, right? Oh, okay, it's here now. Yep, that's very good. Okay, yep. So let's take a look at this one. Yep. So this file is predicted as bulky because it is greater than 39. So and the pi explainer, it is a rule-based technique. It also suggests what is the risk threshold that it should be, right? So I am going to try what if we change the class couple here to something less than around 30 and see whether the risk score will be lower or not, right? Let's try. I'm very excited. Okay. Yep. So it works. That means if we change to the change the value of this this feature to the lower one, the model will predict that this file has a lower risk as well. So sometimes this kind of knowledge will guide developers how small that they should change or how they should update the code. Yep. Okay. Does the range in these visuals represent the potential values? The potential values, it just recommend based on the calculation behind, but at the moment, not too sure. Adida, do you want to ask some questions here? Yep.
Oh, sorry.
What kind of
there's some
potential?
Can you hear me?
Yes, yes.
There's some background noise. Sorry, I meant the range in these visualizations, you know, the 0 to 70, for example, here, that is taken from, and are they specific to a project or general recommendations for where those metrics fall within?
Okay, I see. Yep. So you get the right point. Thanks for the question. Yes, this kind of range is very specific to the file, to the individual prediction, to the instance that we want to explain. So it will not be a generic the most important features like the global level or the model level. Yep. So this is a very specific one. All right. So let me go back to the slide. That's the Pi explainer demo here. Yep. So I am going to take some break, let's say 2 or 3 minutes. And in the meantime, can you please fill out the survey as well for today? And then, yep. And then after that, I will continue the rest of the tutorial. Thank you, everyone. I will keep myself muted. And in the meantime, you can put the questions in. I will answer the next question from John and Vic. Where did the threshold value of 39 come from? So I'm going to explain in the next step, how does the Pi explainer work? What is the algorithms inside? What is the key concept? Yeah. Thank you. So everyone, if you have already completed the survey, can you say like a thumbs up to me? So I know that when we should move to the next slide.
Hi, Clark. Can you perhaps copy and paste the URL for the survey on the chat?
Oh yeah, sure. Jirayut, can you help me? Yep. So yep. So the URL tiny.cc/AI4SE-survey. Thank you. Okay. Okay, 11:30 now, then I will continue to the next part. Okay, now the next step, I am going to explain what is the Pi explainer, how does it work inside, okay? So the key intuition of the Pi explainer is to build a local model to approximate the behaviors of the global model. So normally global model is treated as black box. We don't know how does it work. And that's why we need to develop this kind of technique, which is called a model agnostic technique, to actually explain the behavior of the global model. That means from the global model, we're going to take two input, okay, to the Pi explainer. First is the instance that we want to explain and the global model. So the first step, given an instance to be explained, we want to generate the synthetic instance around the neighborhood. Okay, let's assume that the X here is an instance to be explained around the decision guide, decision curve of the model here. We're gonna randomly generate the neighbors here, the synthetic neighbors, and then we can get the neighborhood here. And based on the synthetic neighbors, we're going to input into the global black box model to obtain the prediction. Okay, so I'm going to call it y dat. Okay, so that means right now we have the features, the x and the y dat, the predictions from the global model for the synthetic neighbors. Then we already know how the behaviors of the global model. Then we're gonna input this kind of data set into the rule fit model. So we choose the rule fit model because it will generate the rules instead of the most important features. Okay. Once we get the rule fit model, then we will extract the rule-based explanation from this model. Okay. So, and the next step, I'm going to explain like how does it compare with the LAM approach, okay? So in general, the general explainable AI concept is to generate the synthetic neighbor, build a local model to approximate the behaviors of the global model, and then it will generate the explanation, okay? But the motivation of this work, the problem is that the quality of the explanation often relies on the neighborhood that are generated and the local models that are built, okay? LAM, which is a state-of-the-art approach, and right now it has been cited more than 6,000 papers. They use just a random perturbation, which is not that smart at all. Given an instance to be explained, they just throw random instance, and then they just build a K-lasso model based on the random perturbation, the random synthetic neighbors. And then they just generate the explanation from this one, okay? But the problem is that when they use the random model, the random techniques, there's no heuristic at all. And the neighbors are too large. They are not specific to instance to be explained. So that's why when the neighbors are not of high quality, it will produce an inaccurate model. And it will produce the poor approximations of the instance that we want to explain as well. That's why LAM is not that effective at all. Then it will produce the incorrect explanation and the incorrect insight. That's the main limitations of the LAM that we want to raise in this paper. Okay, but when compared to our approach, we use the crossover and the mutation to generate the neighbors. That means given in an instance to be explained, it will we start from the initial random seed, random instance, and then we do some crossover using the heuristic of the actual instance to be explained as well, actual data. And then once we have a more effective neighbors, then we use the rule fit model to build the local model, and then we generate the explanation. That's the key difference. But how can we ensure that the neighbors that we have is better than LAM, or the local model is better than LAM or not? So we conduct an experiment to evaluate the quality of the neighborhood that are produced by PyExplainer when compared to LAM and the local model. And finally, the results that we found is that PyExplainer produces more similar synthetic neighbors and more accurate local models when compared to LAM. So it means that our approach actually produce more unique and more consistent explanation as well. So that's the key concepts of the PyExplainer. Okay, I'm gonna pause a little, 1 or 2 minutes to answer some questions if you have. Yep. Now, so Yi Cheng has a question: what is the difference of concepts of the local model and the global model? That's a good question. Okay, so global model is the model that we train from the whole data set. Okay, and most of the global models are very complex. They are built from deep learning. They are not understandable at all. So that's why we need to build a local model to approximate the behaviors of the global model. And the local model will be more interpretable than the global models. That's the concept. Am I answering your question? Yes, thank you. Okay, all right. Then I am going to move to the next part of the tutorial. Okay, the next part so in the part 1, I already talked about the concepts of the explainable AI for software engineering. And the next part, I'm going to talk about what are the other potential usage scenarios of this area. Okay, so as I mentioned again, developers submit lots of pull requests, and reviewers, they have to review the code. But they don't know, but there are too many pull requests, commits, and files. How can we better allocate the limited resources? So defect prediction models are built. And what I am going to say is that explainable AI is not just only to generate the explanation, but it can be used to identify which lines that they should look for as well. So it's called line level defect prediction. And this is what I already mentioned, why it is predicted as risky, and to generate the actionable guidance. What should I do to improve the code quality? So what I'm going to say is that in this presentation, I'm going to focus on the 3 aspects. How can we make defect prediction models more practical, more explainable, and more actionable? Okay, and in terms of the explanation, we can generate like which features are the most important, but we can also generate which lines are the most important or contribute to the predictions as buggy as well. Okay, so in the earlier presentation, I already talked about that PyExplainer can be used to explain the model, but there are lots of types of explanation as well. How can we maximize the benefits of the explainable defect prediction? Okay, so maybe I'll just talk about the motivation a little bit. Researcher, in the 2018, Hua Damador from Wollongong, he raised concerns that a lack of explainability could lead to a lack of trust when adopting defect predictions in practice. And in our recent study, we ran a survey with practitioners to identify what do they perceive. What do they perceive about the goals of the defect prediction studies? And we first do the literature review to identify what are the goals, and we found there are 3 common goals. First is to improve the accuracy, to generate the explanation, and surprisingly, what we found is that practitioners often perceive that explanations are equally useful as improving the predictions. So But the challenge is that most of the machine learning based defect models are globally explained, but they are not locally explainable yet. So, and then the global explanation is often derived from the historical data, but they may not be applicable to the unseen data. So just to illustrate again, you have a data set, you build a model, you extract the feature importance. That's the knowledge or insight that is derived from the model, but not the unseen data. That's why we need a new technique, new concept to make the defect prediction models more explainable. And as already mentioned, practitioners still do not know why a file is predicted as defective. So we in this study, which is published at the IEEE Transaction on Software Engineering, we use LAM to answer 4 types of why questions. Okay, so the first one is that we want to answer why is this file predicted as defective, right? This is an example visualization from LAM. Given this file, what are the features? There are 2 types, supporting explanation and the contradicting explanation, okay? So we're gonna look at the blue one. So in this figure, it shows that this file is predicted as defective because the numbers of class couple is greater than 5. The numbers of comment lines is more than 24, something like that. So it means that to mitigate the risk, we should consider reducing the class couple. Okay, this is an example. And we can also use to answer the property contrast as well. Why is this file predicted as defective rather than clean? So we, based on the LAM explanation, we know the supporting explanation and the contradicting explanation, the red one as well. So like in this one, we know that LAM is predicted as defective rather than clean because the numbers of developers is less than 2. It means that we should maintain the numbers of developers. We should not increase it at all. Does it make sense, everyone? Yes? Okay. And then in thank you. And then we can also use to answer the other 2 types of questions as well. Time contrast explanation, right? Let's say if we build a defect prediction model at the release 1 and release 2, one file given the same file in the release 1 is predicted as defective, but later on it is predicted as clean. Then the question is that why is that, right? So we can use LAM to explain the model in the release 1 and the release 2 as well. And within the same release, we can also study like what are the characteristics of the files. This kind of files are predicted as defective, while the other types of files are predicted as clean as well. So what I'm going to say here is that the model agnostic technique can be used to explain the defect predictions in many scenarios, to many questions as well. And this kind of knowledge are very useful to practitioners. So in this study, we conduct a empirical study to better understand the LAM, okay, for the defect prediction models. So the first question that we ask is that, do different predictions have different explanations or not, right? So the motivation here is that normally global explanation is too general, but what about the local explanation? Are they different? If they are different, it means that the global explanation may not be applicable to all of the local explanation at all. So what we found is that given the same defect models, different predictions actually produce different local explanations. So it highlights the need of the explainable AI tools for software engineering. Okay. And we also asked whether the local explanation overlap with the global explanation or not. And the motivation is that ideally local models should accurately mimic or approximate the behaviors of the global model, right? So we're gonna look whether they are align with the global explanations or not. So what we find is that the top 10 features of the local explanations are overlap with the global, but they are not the same at all. So that means, let's say given the top 10 features of the local one, these top 10, they are the same as the global one, but the ranking, they are different. Okay. And the next question is that are model agnostic techniques rely on the random seed or not? Because this kind of technique is called, how can I say, like perturbation-based model agnostic techniques. It relies on the randomization, it relies on the random perturbation. So the different random seed may produce different explanation as well. Right. So we also evaluate LAM for the defect prediction models. And what we found is that, yes, different random seed produce different types of explanations. So that means to ensure the stability of the model agnostic technique, the random seed should be defined earlier. And finally, once we generate different types of explanation, we send this back to practitioners and we run a survey. How do they feel? What do they think? How do they perceive about the explanation, right? And what we found is that 65% perceive that the time contrast explanations are the most useful. That means the time contrast, it means that when a file, the same file in version 1 is predicted as bug, but they are predicted as clean in the version 2. Why is that, right? So I think they perceive that this kind of explanation is the most useful. And next, I am going to show you the next example about how can we use the explainable AI techniques to make the predictions of the defect models more fine-grained. Okay, so the intuition, the motivation is that lots of researchers already raised concerns that fine-grained defect prediction is needed because most of the models at the moment, they are predict at the file level, the class level, the component level. But at the same time, developers still need to spend lots of effort to locate like where it is, where the bug is in the file, right? So there are lots of challenges in this study to build the line level defect prediction. So let's take an example. We just take one software system. We found that, let's say if we are going to build the back-of-word models, right, to predict at the line level, what we found is that the data set is too large, the dimension is too large. We have like over 200,000 code tokens, the features, and more than 200,000 lines of code. So to build like a machine learning model, it is still not easy. And we also found that the ratios of the defective line is still low as well. That means we have 200,000 lines of code, only 1 to 3% of them are actually considered as defective lines. This is like a finding needles in a haystack. How can we effectively build a machine learning models or AI models to accurately predict which lines are the most risky, right? And when we try to build a machine learning model, it doesn't work at all, okay? It doesn't work because the data set is too large, the class is too imbalanced, and at the moment, I still have never seen any deep neural network to predict at the defective lines as well. So this problem is very, very hard, very difficult, very challenging, and I am going to present next how can we leverage the explainable AI technique to predict defects at the line level. Okay, so the key concept of the line level defect prediction is to build two-step model. We're gonna build the model at the file level and use the explainable AI to localize the tokens at the line level. Okay. So in the first step, given a defect data set, we extract the features. We just use a simple idea, the backup words, the backup tokens. That means how many tokens that appear in that file. Okay, so once we have this kind of data set, we're gonna build the model at the file level, and then we're gonna build a prediction. Okay, just prediction whether this file is buggy or not, and then given this file an instance to be explained and the model agnostic technique. In this paper, we use LAMP. We're gonna take these two input into the LAMP in order to understand which tokens are the most important for this particular prediction. Okay, once we know the tokens, we're gonna map the tokens into the lines, and then we can identify which lines are the most defect prone. Okay, so we can prioritize the most risky one to the top and the least risky one to the bottom. And the results are pretty fantastic. You know, we achieve the highest recall. That means we achieve around 61% recall, and the models also produce the ranking of the defective lines very well as well. And we also evaluate with the state-of-the-art approach using multiple techniques, including n-gram and the static analysis. We found that our approach outperforms all of the baseline for both within release and the cross-release settings. Okay, and because this topic is very challenging, it's not easy at all, so we produce the benchmark data set. So if someone have a better idea, who are an expert in the deep learning or AI, they can use this data set to improve the accuracies of this paper as well. So in general, what I'm doing here is it is the results from the research project, my own research project, which is funded by the Australian Research Council. I think the key aim is to invent the next generation defect prediction technologies. It has been proposed for a while, but how can we make it more practical and more explainable and more actionable as well? I tackle industry-related problems. First, developers still spend lots of time to identify where the bugs are. So we build the line-level defect prediction. And when developers still do not trust, we conduct a survey study, make the defect prediction models more explainable. And the last part is the actionabilities. Developers still do not know what should they do to improve the quality of the bugs, of the files, of the predictions. So we propose lots of approaches to make the defect prediction models more actionable as well. Yep, that's all. Before I am jumping to the next part, any questions that I should answer? Let me look. Yep, I presume this is not cross-project, train within project. Yep, nope. So we do both within and oh yeah. I see what you mean. Yes, not cross and not within project and cross project. This is just only within release and the cross release. Yeah. Yep. Any questions? If no question, then I will move to the next part, the lesson learned and the open questions. Okay. So in the first two parts, I already demonstrate lots of usage scenarios of the explainable AI for SE, which is very modern. But I just want to say that the explainability is not something that new. Okay, it has been raised for a decade already, but it's not there yet. So so in the past few days, I just look at I do some literature review and try to do this kind of timeline mapping. Okay, At the 2010, actually Zynga, which is a game company, very, very famous at that time, they already start talking about actionable analytics. How can we make the software analytics more actionable, okay? And then in the ASE 2012, Tim Menzies and Thomas Zimmerman organized a goldfish bowl panel talking about software development analytics. And at that time, lots of practitioners and industry people, they already raised concerns about the explainability. Okay, and later on, 1 year later, Tim and Tom also organized a special issue about software analytics as well. And they mentioned that software analytics must be real-time and more actionable, right? So this is more like a concerns that are raised, okay? But at that time, back to during 2010 to 2015, we still do not see any research that tackle this area, okay? And in 2015, Kristen Bird, Tim, and Tom also wrote a book about the art and science of analyzing software data. So basically, we just start the age of how can we improve the machine learning modeling process to make the models more accurate and more explainable, right? And during my PhD study, I also published lots of papers about and raised concerns about the mislabeling data, the correlation, about the feature selection. Lots of techniques or experimental choice actually have an impact on the model explainability. And later on, people also organized a special issue as well, who in 2018 wrote a short paper at the ICSI near track about the explainable software analytics. And recently, I also raised concerns about actionability as well. So as you can see, there are lots of researchers raised concern, but we are not really there yet. Like, how can we make the deep learning more explainable, understandable to end users, build a better trust, this kind of thing, right? Yep. And early days of the explainability in SE, let's say like this is like 20 years ago, 2000 to 2015, right? There are lots of researchers often use like white box technique or transparent machine learning, like linear regression, nonlinear regression, or using ANOVA naive-based association rules and decision trees to build a global interpretable model, right? But this kind of technique, yes, they are understandable, but the problem is that they are not accurate and they are not locally explainable at all. They just build a data set, prepare a data set, build a regression model, evaluate the R-square. And most of the time, R-square is relatively low, let's say less than 0.2%, right? So that's why in the past 5 years, there are these kind of people like Prem, David Lowe, Dennis, Gabriele, Bavoda, or Max, they tend to use like a AI or more complex model like a deep belief network, MLP, and lots of architecture to make the AI models more accurate. But these kind of models are very accurate, yes, but they are not explainable at all. So how can we bridge the gap, right? Like how can we make these kind of models more explainable? Yeah, and we also talk about let's take a look at the defect prediction concept, right? People, there are lots of researchers propose lots of technique. So in this study, we want to investigate what do practitioners think. What we found is that the practitioners perceive that the three goals are similarly useful, right? But when we look at the systematic literature review, look at the study at the literature so far, we found that 91% of the study only focus on the improving accuracy, like too much incremental improvement already. But there are only 4% actually focus on the increasing the explainability. So how can we make the AI for SE models more explainable, right? And this is not just only the practitioner survey, but as I already mentioned that there are lots of researchers talk about explainability and the actionability as well. Like on the left-hand side here, these are the case studies of the defect prediction models in practice when they are deployed, and what are the feedback that they get. And most of people, most of developers just raise concern about how can we make defect prediction models more actionable. And yet again, researchers as well. So the key takeaway here is that I just want to say that explainable AI is much needed in software engineering, including other software engineering tasks as well. But at the moment, it remains largely unexplored. So how can we make the community, how can we develop more research in this area, right? There are lots of things to do. And the next thing that I want to say here is that at the moment, because the field explainable AI is quite mature now, there are lots of open source toolkits like AI explainable, explainability 360, the tool from Microsoft, Interpret, or PyTorch, Captain. There are lots of tools, okay? But when we look back to the theory of the explainable AI, it means that they want to, it is the term explainability is defined as the degree to which a human can understand the reasons behind the prediction, right? So normally explanation is used as an interface between the humans and the machines. So, and then there are lots of research from the social science or psychology. They run a survey and they found that an explanation is an answer to a why question. And there are lots of types of why questions as well. There are lots of questions that need to be answered. So there are lots of challenges here. First, the effectiveness of the explanation depends on the questions asked. And the explanation can be presented in various scope and various form to serve a goal as well, right? And as already mentioned, different techniques also produce different forms of explanation with different types of information as well. Then the next question is that, no, this is a challenge, yeah. And the next, and different stakeholders also have different questions as well. For example, given a complex AI models, they'll ask lots of questions. Why am I getting this prediction? And because the end users who affected by the decisions also have, we have many stakeholders who is the end users of the complex AI models, right? As a software engineers who take the defect prediction, they also ask one set of questions. Why a file is predicted as defective and how can we make it better? And AI expert also ask like, which AI model should I select, right? Let's say they build 10 highly accurate models, but how can they monitor or debug or select which models should be deployed in practice, right? As a domain expert, they also ask are the AI models learned correctly or not? Is the AI model logic reasonable or not, right? Like, for example, in the image classification to classify a dog or a cat, what if we explain the model and we found that they use background as a classification features? It doesn't make any sense at all. Same to the defect prediction. What if the model use the blank lines as a feature, right? So that means these kind of models are not trustable. So how can we, so the explainable AI can be used to develop appropriate trust and debug the model, help the software engineers understand as well. And the explainable AI can also be used to help like a business leader and policy maker and the regulators as well. So what I'm going to say here is that different stakeholders have different questions which require different types of explanation. And each explanation can be presented in many forms and many scopes. But the challenge here is that most of the XAI toolkits are algorithmic driven. They are built for researchers, but they are not yet human-centered yet, right? So in the future, I think that the explainable AI for software engineering should be human-centric. How can we make the explainable AI tools that are designed by humans. Also, how can we design the explainable AI tools that generate explanation that most suit practitioners need? Okay. One of the approach that we can do is called do-re-mi. Okay, this is one simple approach. The first step, we need to do the domain analysis to understand the AI problems, the social context, and the stakeholders. Who do we want to explain? We need to identify first whether we want to explain the AI models to the developers or the AI expert, right? Then we do the requirement elicitation to understand what are the practitioners' need, what is their purpose, what do we want to explain, right? And then we can design the explanation model, like what are the scope, the models and the forms, and select the tools. So just to wrap up, the second key lesson learned is that human-centric explainable AI approaches must be used to design the explanation that most suit practitioners need. Yep. So that's all for my tutorial today. Now I think I will go back to the question again. For within project. So I have the question from Ali. For within project, how do you split your training and testing data? Is this a time order process? Yes. So for that paper, we built the release-based defect prediction models. That means the earlier release we use for model training, and the later release we will use for testing. Yeah. But we also have another kind of another paper is called Jitline, which is built based on the time order data. And yes, we sort the data set by the time and use the older commits for training and the later commits for testing. So they are not mixing. Yeah. Thank you so much for your question. Thank you. Yep. So if you have any question, feel free to turn on the camera and speak. Yep. I'm happy to answer any question. And again, if you have time, please take 1 minute to complete the survey as well. Thank you so much. All right. So everyone, next, I think the tutorial is already finished here. And the next step is going to be the hands-on exercise. Yeah, the hands-on exercise. Stop share. Let me share my screen again. Yep, the hands-on exercise. So Jirayut, are you ready?
Yes. Should I share my screen or?
Yes, you can.
Okay, sure.
Yep, you can. Maybe just want to check again. Any questions? Any more questions? Okay, no more questions. Then, yep, I think we can move to the next step. Okay, the next part of the tutorial is which is the hands-on exercise. Yep, over to you, Jirayut. Yep.
Okay. Let me share this screen. Okay. So I'm going to use Binder to interact with this exercise. And so this exercise have 4 main parts, but we are going to focus on 3 of them first, because class has already covered the PyExplainer part. Please wait a bit. Okay, so everyone can follow the exercise by using their own interactive notebook, or just walk through with me. Okay, so the first part here is to set up the environments. So when explaining any instance, first you need to prepare the datasets and the model. Here, we have already prepared some basic codes for you. So let's start with the first one. Okay, constructing random forest. This one, we can simply skip this one. And here, so first is lam, and the second one is chap. I want to emphasize that these are very simple. You can explain them using only 3 steps. So basically, first you need to build the explainer, and then you can use that explainer to explain each specific file or prediction. So let's start with the first step. Okay. So for example, lam, you can just simply input the training data, which are our extrain, and then you select the mode of the explanation. lam can handle both classification, regression, or other types of input, for example, text as well. You can explore more in the document page of lam repository. And then we need the label, and then the features name and class labels, and I mean, you can, if you want to know what kind of expected input, you can print each of them in your own notebook. Now, so we have our lam explainer here, simple in 1 line. Then we will use this this explainer, our explainer. Oh, here. So we will use this our lam explainer to explain instance. And what we need for this function is the row that we want to explain. In this case, here, we want to explain this documents writer, right? So we need to replace this one. And then we need the predict function of our our black box model. In this case, it's called it is our RF model. And then we need to specify how many features that we need to we want to explain, and then we run this one. Okay, done. And now to visualize this lam local explanation of this instance, we can simply use show in notebook function. Then lam will automatically generate the visualization. Okay, so now we can see that lam is still working on generating the explanation, and it should not take long. I hope. At least that's what I discovered when trying this notebook. Okay, we'll go this does not happen when I test the notebook. But okay, so let's imagine that we have LAM visualization and let's try to move on to the next one. Okay, but what I'm trying to emphasize here is that it's only 3 lines of code, and maybe the data set is too small because this is just a sample data, or it has some problem with this environment. But you can try to explore more in your environment. It may work for you. And let's move on to the next one. Okay, so here for SHAP as well, you can simply explain in 2 steps. No, 3. 2. The first one is you need to construct the explainer similar to LAM, and to do so, you just input here. The expected input for this function is your model, the predict function of your model, and the data that you want to explain. So in our case, is our RF model and X test. So here we are done with the first step, and then we can move on to the second part, which is generating the explanation for the file you want to explain. So to do so, you just use the explainer and then use the SHAP value function. The expected input for this one is the instance that you want to explain. And my notebook is very weird today.
I think, yeah, this is the binder problem because we use the free resources. Normally, if anyone run the Jupyter notebook at home, it will be much faster, yeah, than the binder.
Yeah. So I'll copy it here because I don't want to the binder to repeat this line again. So here you can generate the explanation for this specific file with just with this simple function. And after you have that this explanation, to visualize using SHAP, you just use the force plot function. Actually, SHAP also present other forms of visualization, which you can explore in the repo page. But here, you take this instance here to replace what you want to visualize, and then press. Okay, oh, here. So here you can see that SHAP generate the force plot for this documents writer.java. And here in this example, you can see that the predict probability of this file being defective is 1.0. And the 3 top supporters, the 3 top variables that contribute to these predictions are count class couple, own commits, and added line. Okay, here the PyExplainer. Okay, we still have time, so I'll try to cover this one as well. Similarly, you can explain this the file with PyExplainer with only 3 simple steps. So first, you construct the explainer. The expected input for this one are the training data for both independent variables and the outcome or the feature on the dependent variables. And then you just input the column names of the independent variables, and then you need the black box models. So in this case, the name is our RF model, and then this one should run fine. And then after you have the explainer, you similarly explain the instance with this with this function. So it's called the explain function, and the expected inputs are first the instance that you want to explain. In our case, is document writer.java. You just input it here, and then the level of this file that you want to explain. Then you select the search function, max the number of max iteration, number of rules, and so on. Okay, and then you run it here. And finally, after you have the explanation to visualize the PyExplainer explanation, you just take the instance, the explanation of this instance, and then you visualize with this function. Okay, this may take a while, so I will move on to the fourth one. So the last one is a bit tricky here. Please use LAM to generate the object contrast explanation between document writer.java and teststring intern.java. So in the presentation, class has already covered several types of contrast explanations. For example, property contrast, time contrast, and object contrast. So to recap that definition, object contrast is the contrast between two objects. So in this exercise, we are going to generate two explanations for document writer and teststring intern, and try to compare and contrast between the two of them. Okay, so it seems that Biner is still working on this cell. So I will first prepare some code. So I will go back and take the code from this one. Okay, so we have already finished the first step here, because here the first step is very simple. You construct the explainer with this one, and then you need to generate the prediction for the first file and the second file that you want to compare with the first one. And to do so, we need two lines here. Let me go back. Okay. Oh, here, PyExplainer is done with that job. So here you can see the explanation here. So the risk score here is the predict probability of this file being defective. And here you can interact with the visualization, and it will try to regenerate the predict probability here. So if you lower the added line and count class couple, you can see that the predict probability of this one being defective is reduced to 7%. And that is the basic idea of what is visualization of PyExplainer. Now, so here's how so of the first instance. So the first one is the file to be explained, right? And the second one is here, the second instance. Executing these two lines, you can generate the property contrast of documents writer and teststring intern, and to generate the object contrast of these two files, you need to visualize both of them. So to do so, let me go back and have a look on how to. No, here. Okay, so it's very simple. It's just a show in notebook. So first, you need to show in notebook for the first file here, and you also need to show in notebook for the second one. Okay, so it works now. I didn't make any changes for the first file was the same file with the previous rows, previous cells, but yeah, please go ahead.
天哪，我刚刚看到上次我不是说在那个买 PPT 那个美声 C 那个什么吗？对啊，差点的。他现在发给我说到
Can you please ask again in English, please?
Should be fine. I think someone is unmuted. Yeah, please go ahead.
Okay, sure. So here we can see that in cell number 12, we can see the property contrast of the first file or documents writer. It says that this one has the predict probability of being defective for 77%. And the three main reasons are here. Similarly, for the second one, this one has a second instance. I made a mistake. I need to change. Okay, sorry. I will regenerate the explanation. And if it is done, then we should get the explanation for the second one. But basically, you get the idea. When to generate the object contrast, you just generate two property contrast of the two files. And yeah, basically that's it. That's all. Oh, here we can see that for this documents test string intern.java, this one is likely to be clean with the predict probability of 90%, and the main reasons are these four values. And that's all for the hands-on exercise. Thank you very much. Now passing on to Clark.
Hello, thanks, Chirayut. Yeah, I think we did great. The hands-on is successful.
Yay.
Yep. So I think maybe I think I'll just open the opportunities for the audience. If you have any question, please feel free to ask me. Questions? No? Then, yep. Yep. So maybe I will just wrap up. Okay, I think we did great. We have 2 more minutes. So anyone in this tutorial, could you please complete the survey tiny.cc/xai4se-survey? Yeah, any feedbacks or comments I really appreciate. Okay, so just want to wrap up the tutorial today. We make lots of we discuss a lot about how why the explainable AI is very important in software engineering and how can we make it useful. We also discuss about the potential usage scenarios, about how can we make the defect prediction models more practical, more explainable, and more actionable. So if you are interested and if you would like to learn more, please feel free to go to our book, xai4se.github.io. If you want to run any code, just go to here and click just launch the bidder, and then you can enjoy. Yep. So in this tutorial, we talk about what is the theories of the explanation, and we talk about what are the techniques to generate the explanation. We also discuss about like how can we use LAM to explain the models. And with some example code as well, chap and the Pi explainer here. So that's all for the book. If you like it, please let us know as well. We would love to hear the feedback. Yep. And if you have any questions, please send me an email, follow-up email. We can discuss, we can collaborate, we can think about how can we make this area more active as well. Yep. Thank you so much, everyone, for coming. Yep. Bye-bye. Have a great day, everyone.
Thank you.